So yesterday we were talking about velocity versus time graphs. Okay, we started looking at a little bit of stuff to do with that. So I just want to kind of review and go over a few more examples of velocity versus time graphs, calculations that you might be asked to do from those. And then we're going to start looking at the lab that we're going to be doing on Monday. Okay, and that's kind of where we'll end off today because it's a short class today. So what I would like you to do to start off with while I get the attendance done is give this question a try. It's a velocity versus time graph. These are exactly the calculations we worked on yesterday. Okay, I want you to calculate the total displacement and the average acceleration over the whole trip. Okay. All right, so for the first part, we got to find the displacement. We talked about yesterday how if we want displacement from a velocity versus time graph, what we really need to do is take average velocity and multiply it by time, which generally comes out to finding the area underneath the line. Okay, so we have this first part where the object travels at a constant or average velocity of 3 meters per second for 4 minutes. Did anyone notice it was minutes? Did you convert it to seconds? I didn't even notice it was minutes. Okay. I'm going to do this because it's quicker. All right. If you converted the minutes to seconds, you're still fine. Okay, it's the method here that's important. Okay, so 3 times 4, okay, that's going to be 12 meters. Then we have this part of the graph where the object slows down, which is an acceleration. Okay, it's just a negative acceleration, and that means that it's going from 3 meters per second to 1 meter per second. All right, so the height of this triangle is 2, okay, and the base of it is 1 second. So 1 times 2 is 2, divided by 2 is 1. Okay, and then we've got this rectangle here, okay, which includes the area underneath the acceleration portion where the object would have been traveling at an average velocity of 1 meter per second for the remaining 6 seconds. So that'll be 6 meters there. All right, so we're looking at, 19 meters? Yeah. Okay, in total. Are they all right with what we did there? Now, for the acceleration is quite a bit easier, okay? It's not a constant acceleration because there's, 2 parts where it travels at a constant velocity. So we just use this formula. We can't use y equals mx plus b because it isn't one single function. So all we have to do is go 1 minus 3 over 10 seconds. Okay, so we got negative 2 over 10. So our average acceleration is negative 0.2 meters per second squared. Okay, everybody okay with that? Is the negative important? It is. Okay, this acceleration is a vector quantity, so we need to make sure we include that. Okay. Now I want you to look at this graph. Okay, I always ask a question like this on the unit exam because it really tells me who reads and interprets graphs the best. Okay? It's kind of my question that separates the wheat from the chaff kind of thing. So in this graph, okay, the first thing they want us to do is determine whether acceleration is positive, negative, or 0 in each section. All right, so in section A here, is the object accelerated? It is. Okay, this is a velocity versus time graph, and the velocity is changing. Now, I know a few of you are going, CoderreScience, going backwards. That's fine. The definition of acceleration is any change in velocity over time. In physics, we don't use the term decelerate. Okay? Everything is an acceleration. It's either positive or negative. Okay? In this case, this is a negative acceleration. It's actually speeding up backwards. Okay? So it'd be like if I was trying to run backwards. And then in part B, what's the object doing? Right, staying at a constant velocity of negative 4 meters per second. And then in part C, it accelerates negatively again. So it's going faster in a backwards direction. Okay, it goes from negative 4 to negative 6 meters per second. And then in part D, constant velocity of negative 6 meters per second. All right, what's happening in E? accelerating positively. Okay? And then what's going on in part F? Constant velocity, right? Okay, here's the tricky part of this question. At what time does the bird, because this is supposedly of a bird, change direction? Because obviously for part of this graph, it's flying backwards, and for part of this graph, it's flying forwards. At what time does it actually change direction?
At like the 8.5 area at time?
Right here?
5 seconds, yeah.
Exactly. How many of you wanted to say it was right here? Okay, because that's when we see the line change direction, right? And that's kind of our gut instinct, and that's why I use this question as an example. Okay? Is the bird's velocity here still negative? Then it's still moving backwards. It's moving backwards as long as its velocity is negative, which it is until it gets to right here. And then its velocity becomes positive. All along this line, its acceleration is positive. Okay? So essentially what's kind of happening here is, it would be like if I ran into a bungee cord. Okay, so if somebody put a bungee cord across the front of the classroom. Hey, I'm running forwards. Okay, I hit the bungee cord. I'm still moving forwards, but I'm accelerating backwards, right? Because my velocity forwards is now decreasing. Okay, I get slower and slower and slower until I start getting shot backwards by the bungee cord. Okay, but my acceleration doesn't change. It's always backwards, and as long as the bungee cord is pushing on. Does that sort of make sense? So that's kind of what's happening here with the bird. Okay? It starts to accelerate in the other direction, but it's still moving backwards until it gets to here, where its velocity, at least for an instant, is 0, and then becomes positive. It would be the same if I threw this up in the air. Okay? The entire time, the acceleration, like the graph of that motion, the velocity versus time graph of that motion would look like this. Okay? The slope of that line would be 9.81 meters per second squared. All of this part here, sorry, I'm not ignoring you. Who had their hand up? Okay, somebody else had their hand up too. No, okay. All right. So we got, during this whole part here, the object is moving upwards, but it's accelerating downwards. It's not until it gets to its maximum height, where it stops for an instant, that it actually starts to fall and have a negative velocity.
Somewhat answered the question.
Oh, okay. Somewhat?
Somewhat.
What's the part I didn't answer?
I'm just still kind of confused with the bungee cord analogy. How can your acceleration be negative if you're still moving forwards?
Because I'm going slower and slower forwards. Once I hit the bungee cord, it starts pushing me backwards, which slows me down. So my acceleration is negative because my forward velocity decreases. Does that make sense?
So even if you're not necessarily going backwards yet, it's like going from 7 meters a second to 4, it's negative acceleration.
Right. Okay. And the same thing for this, right? When I throw it up in the air, it's still moving upwards, but its acceleration is downwards the entire time once it leaves my hand. Yeah? All right, so that one kind of makes sense to everybody? Okay, so that's one of those ones where you have to really read the graph carefully, because your gut instinct is to go with the line change direction, it's right there, okay? And it's just a natural instinct for us to say that. Okay? We have to have that better understanding of the graph. Okay. I don't think I had any more that I wanted to do. Nope. No. I didn't have any other good graphs. No, I didn't. Okay. So let's have a look at Google Classroom here real quick. Okay, so if you guys can pull out your phone, because I didn't get the Chromebooks for today, okay, but I do have the Chromebooks for Monday. Gonna need you to do a couple of things. Okay, the first thing I'm gonna need you to do is find this app in the App Store. Spark View, spelled V-U-E. Okay, it's free. I think there is a paid version, don't get it. Okay, the free version works just fine for us. Okay, that is the app that will allow your phone to communicate with our Dynamics carts. Okay, our new Dynamics carts have internal electronic sensors, and they communicate via Bluetooth with your phone, and they will transmit all the position, velocity, acceleration, and time data with your phone automatically. It's really sweet, okay? Because we used to have to do this with like ticker tape. It took forever. You have to measure all the little dots on the little piece of paper. It was ridiculous. You had to count them too, because each one of them was 1/20th of a second or something. It took forever. Anyway, this is way better. You got really lucky, like practically plots the graph for you. Okay, so that's the app we'll be using. Okay, on Monday. So as long as at least most of you have it, so there's only one person per group who's going to need it. But, okay. All right. So the way this lab on Monday is going to work, okay, is we are going to have these little Dynamics cards that you can see here, this blue one, okay, and we're going to just put them on a track. And we're going to give them a little push, and then we're just going to record the data that occurs while they're moving at a constant velocity, which they will for a very short period of time, but it's enough for what we need. Okay? So we're just going to give them a little push, and then record the data as they travel along the track, okay, at a nearly constant velocity. Is it perfectly constant? No. I mean, they accelerate a little bit when we push them, obviously, and once we're not pushing them, friction is trying to slow them down. Okay? But we still get at least close enough to a constant velocity for what we need. Okay? So we'll do a couple of trials, give it a little push, give it a bigger push, give it a harder push, okay, so we get slow, a medium, and a fast kind of thing. Okay? So what we're going to be doing with that data is this. Okay? We want to be able to calculate the speeds of these carts using a position versus time graph. Okay? So we're going to be collecting the position and time data for these 2 trials, or 3 trials, whichever we decide to do. Okay? And then we're just going to plot position versus time graphs for both, and then we're going to get the velocity from that graph, and then we'll do a couple of little calculations like I showed you yesterday. Okay? Remember I said this is going to be exactly what you're going to do in your analysis, and we'll do that. Okay? So it's a pretty straightforward lab. Okay? We're just going to be recording position and time, plotting a position versus time graph, okay, and doing some analysis. Right? But just a reminder here, lab report format, okay, kind of what my expectations will be for you. Okay? In your version of this, okay, so it's already in the classwork tab because I posted it this morning. Okay, you'll see position versus time graphing lab in here. Okay, if you click on that, you'll see a bunch of different files. I'm just going to open the whole assignment here. So there's a PDF, which is basically what I'm working off of off the smartboard here. Okay, there's a YouTube video, which is my explanation of the lab and basically all the stuff I'm going to kind of do right now and again on Monday morning. Okay, and then the data. Okay, now you're not going to need the data if you're here on Monday. Okay, if you're here on Monday, you're going to have your own data, and that will be better. Okay, this data is just there in case people are sick and can't be here. Okay, so then they have data to use. And then this is the most important part. This is your lab report right here. Okay, it doesn't say student code error, it has your name on it. Okay, so if you open that up, we'll talk about some of the stuff that's got to go in there. Okay, so the first thing that has to go in there is the problem. Now, I've put a problem here. Okay, how can the speeds of 2 different toy carts be determined? You kind of just need to restate that in your own words, in the form of a question, so it's kind of like Jeopardy. Okay, because the problem is always a question, right? So something about how the velocity of a cart can be determined with a position time graph. Okay, I'm not terribly picky about the problem, as long as it's not there, and as long as it's not word for word what I wrote. Okay. Then you're gonna have your design. And in your design, you are gonna have your manipulated, responding, and controlled variables. And you need to explain each one. You can't just say, the manipulated variable is time. Spoiler alert. The manipulated variable is time. Maybe you wrote that down. Weird. Just kind of giving you an answer there. Anyway, then you need to give me an explanation. So don't just say the manipulated variable is this. Okay? The explanation needs to include a couple of things. Okay? First off, how is time being manipulated? And how it will affect your experiment. Okay? Specifically, how will it affect your responding variable? So, to give you an idea of what I'm looking for, I'm going to tell you the rest of the answer for the manipulated variable. I want to write it down. Okay. So, time is the manipulated variable. Time is the manipulated variable because the experimenter is determining the length of the experiment. Of the experiment will affect how far the cart can travel. So anytime you're doing the variables, okay, whether it's manipulated, responding, or controlled, okay, you need to identify and explain. And in the explanation needs to be a why and a how, basically. Okay? How is time being manipulated, and why will it affect, or how will it affect the experiment? Okay? So with your responding variable, you'd say the same thing. This is the responding variable because it's responding this way to the manipulated variable. Now, in this lab, there's only going to be one responding variable. Sometimes you'll have more. Okay? In this lab, there's only one. Okay. And then for your controlled variables, you need to list 3. Now remember, your controlled variables are the things that you have to keep the same, or at least do your best to keep the same or constant, okay, throughout the experiment, so they do not affect your responding variable. So in this lab, we want the velocity of the cart to be constant. That means we don't want the velocity of the cart to change, or we'd like it to be controlled throughout the experiment. Okay? Then you would have to talk about how you would control it and how it would affect your responding variable. Now, I haven't told you what your responding variable is yet, but you are going to be building a graph in this lab, and that graph will be of position and time. And what usually goes on a graph are your manipulated and responding variables. Okay. And so, basically in this experiment, anything that can affect the velocity of the cart needs to be controlled. You've got to come up with 3. I've already given you 1. Okay, we know the velocity is a controlled variable. Okay, what are some other things that could affect the velocity, and how are you going to control them as the experimenter? Okay, so you got to kind of look at our setup. Okay, the setup is we're going to have these tracks on the floor. Okay, and the carts are going to be on them. Think about anything that could affect the speed of the cart and how you're keeping that so that it won't, or doing your best to make sure it doesn't. All right, so that part is worth 5 marks. Okay, the variables are worth 5 marks of the lab report. The lab report is at 30. It's really important to have your explanations there. If you don't explain your variables, the best you're going to get is 2, and that's if you actually identify them all correctly. Okay, the explanations are worth 3 out of 5. All right, after that, you're going to have your hypothesis. Okay, a hypothesis should be an if, and then statement. Okay, the if part kind of talks about the problem. Okay, the and part describes the experiment, and the then part talks about your expected findings. Okay. So for this lab, right, we're wanting to calculate essentially the speed of the of the carts. Okay, so the if part should probably talk a bit about what the relationship is between position and time for something traveling at a constant velocity. Okay, there's a certain kind of relationship that we would be looking at. Okay. So you could say, if there's this kind of relationship between position and time, and then you describe the experiment. Carts are allowed to travel along a track for a short period of time at a constant velocity. Okay. The then part needs to tell me, how are you going to get the speed? Okay, or in this case, velocity. They're the same because it's linear. Okay, so the then part needs to tell me, how are you going to get the velocity from your position versus time? How are you going to get the velocity from your position versus time graph? Okay, that's something we did about a half a dozen times yesterday. Okay. Now, the key part of that, guys, is that you're getting it from the graph. That means you are not doing that. Okay? Because a lot of people, that's what they do. They spend all this time and effort, they build the whole graph, and then they just look at their data and they take the last distance and the last time and go v equals d over t and think they're done. Okay? That's 1 point out of, you could have like 100 points on the graph. Okay? If you have 100 points, should you use all of them? You should, and I don't mean do v equals d over t 100 times. I mean use your graph. There's a part of a position time graph that calculates velocity for you. We learned how to do that yesterday. Okay, that's kind of what we're looking at here. Okay, when you do that, you're taking into account all the points that you recorded, not just the last one. All right. Questions so far? So then the procedure, like we said, pretty straightforward. Okay, we're not actually doing it this way anymore. We used to do it that way, but these work way better now that we have the Bluetooth carts. Okay, so we'll just have that, and the cart will travel along. Now, for the analysis, okay, it's pretty straightforward. Okay, you're going to plot a position versus time graph that has both carts plotted on it, and using y equals mx plus b, determine the velocity of both cars. Okay, so on yours here. Okay, so insert your data charts and graphs. Okay, determine the velocity of both cars. That's it. This is a short lab. Like literally, you should be able to get this done in class on Monday and have no homework. And just, yeah, you're building a graph which you already know how to do, and I'm not really even asking you to do anything with it. And I forgot I changed this, so you don't even have to do the find y and find x parts anymore. Okay, so it's super short. Okay, then you've got your conclusion. So for your conclusion, copy and paste the hypothesis. Okay, so just take your hypothesis, copy, paste it. Okay, and then tell me, can you accept or reject it based on your data and analysis? Okay, so you don't just go, here's my hypothesis and it's good. Okay, or I accept it. You have to say why. Okay, I accept it because the shape of the graphs looked like what was predicted. You know, the calculations performed in the analysis clearly show this type of relationship, and you know, this part of the graph was equal to velocity, and explain why. Okay, just have some explanation there. Your conclusion is worth 4 marks. Okay, so you need to have 4 marks worth of stuff, and that's not just a copied and pasted hypothesis followed by I was right. Okay, like we have to have a little more than that. Okay, in your evaluation, which is out of 3 marks, okay, you identify 2 sources of error and give me ways to fix them. You're not going to hurt my feelings by finding things wrong with the experiment. Okay? We know that inherently there are things wrong with the experiment. Okay? There's very little that we can do about that. We want you to find those things. Okay? The best place to look for sources of error is your controlled variables. Okay? You're going to say in the controlled variable part, this is a controlled variable, this is how it was being controlled. Okay? In your evaluation, you want to say, this is how it was controlled, but it wasn't perfect, and this may have still affected it in this way, and here's how we could fix it. Okay? And that how we could fix it doesn't mean you actually would have to be able to do it. Okay? Just say, this is there. Fixing it might involve having to do something like this. It doesn't matter whether we have the money or means to do it. Okay? Just what would you do? If you could do anything, what would you do? All right, are the expectations pretty clear there? Okay. So on Monday, we will have the Chromebooks, okay, and we'll have the little carts, and we'll have the phones and the tracks and everything, okay, and we'll kind of just get everything going. We do have to make sure that when we're done with all the equipment, that we take out the sanitizer and spray it down and all that kind of stuff, okay, afterwards, so that the next class can use it. Okay, and obviously, when you're working together in a group, everybody will have to be masked up and all that good stuff. All right, so the marks go as follows. Okay, the design, so that's your variables, 5 marks. Hypothesis is 5 marks. Your data is 3 marks. Okay, your analysis is 5 marks. Your conclusion is 4. Evaluation is 3, and the overall quality of the report is 5 marks. Now, what goes into the overall part, guys, is things like grammar and spelling and appearance. Okay, if you're like, and there's really no reason for this to happen, but if for some reason your report doesn't follow this format, which it better because I laid it out for you, okay, all you have to do is fill it in, okay, that would, you lose marks there. If when I open it up, it looks like it's bleeding because so much of it is underlined in red for spelling, that leaves me with a poor impression, okay? That would cause you to lose overall marks. If your grammar makes it difficult for me to understand what you're saying, that could also, okay, cause you to lose marks. Okay, try and be as succinct and clear as possible, okay, when you're writing your stuff out. Okay, so that's kind of what I'm looking at for the overall part. If parts of it are missing, that affects the overall mark as well. Okay. All right. Questions from you guys? Okay, everybody's good with that? Okay, so that is what we'll be doing on Monday. Now, this is what I want you guys to work on now that we actually got through that. I didn't know if we were going to get through that or not, so. Okay, so using that graph there, guys, I would like you to try and answer those questions there on the velocity versus time graph. It's more involved than anything I would obviously give you on the test, okay? But it's just good for practice. Okay, so let's have you guys try that, and then we'll have you try the last question because it's kind of a tricky V equals D over T thing. right, let's just take a kind of a quick look over a few parts of it here. So if we want to find the total displacement over the whole trip, is that a ton of shapes that we got to calculate? Yeah, it's a lot. Okay, but as long as we know that it's that it's all these shapes, okay, we can get it done, right? I would say probably you got. I would do a rectangle, probably just to here, and then do this. Whoop, sorry, not to there. To here. Probably look at this triangle since it goes all the way to the bottom. So I'd have probably something like that for the part that's above, and then probably like this triangle. Probably something like that. I would say that would be the least number of shapes you could probably do it in. Okay? And then you have to find areas of all those shapes and add them all together. Now, the trick to this one is, yes, I add them all together, but some of them are negative. And I have to keep that in mind, right? When I'm calculating the displacement, that's the area of these triangles that are below the x-axis, sorry, they need to have negative numbers, okay? Because during those parts of the graph, I am going backwards. So I'm retracing my steps, and that is going to affect my final position. All right, average velocity over the whole trip. Well, once we had calculated the total displacement here, then we just have to do this. Okay, we'd have that number, it'd be the area of all the shapes added together, divided by the total time, which is 22 seconds. Okay, so we'd be that total displacement over 22. Okay, acceleration between 10 and 15 seconds. So that would be for this part right here. Okay, that'll simply be an A equals VF minus VI over T calculation. So we're going from 28 to negative 12, so negative 40. We have negative 40 over 5 seconds, so it should be negative 8 meters per second squared. Okay. Acceleration between 6 and 10 seconds. Okay, so that's starting here and going to here. Okay, so same calculation, A equals VF minus VI over T. It would just be 28 minus 12. Okay, so 16 over 4 seconds, so positive 4 meters per second squared. Okay, distance traveled between 0 and 10 seconds, you'll have already done that, or at least part of it. Okay, so you're just calculating the shapes there. Okay, average speed, total distance over total time. Okay, so nothing like mathematically challenging, it's just tedious. Okay, it's like a tedious calculation on it. Okay, all right, how are we feeling about that stuff? Okay, I would expect that Tuesday's quiz will probably have a position versus time graph question and a velocity versus time graph question on it, because that's what we're going to be working towards. Okay. All right, so be ready Monday, we're going to be doing a lab. Okay, and we'll hopefully get it all done. It shouldn't be a huge amount of homework for anybody in class. Because we got all the pre-lab stuff essentially done. So I can go over that real fast on Monday. Okay, let's have your pack up, mask up, and then come around and spray off your desks.